Fine. Yeah, so last 2-3 lectures we have discussed a lot of things related to the system, related to the controller design and all these things, assuming that the most important component for running our motor drive, the power converter, is there in place. Now, again, if I refresh your memories, the three important components, so the power electronics, and connect it with the machine, and then the load and controller. So these three components we have been discussing, and we have seen that the load dynamics, how it is related to the stability and instability of the system. Then we have seen how to design controller for a particular case where we had DC motor which was separately excited. So for this particular system, we have designed the controller. Now, one assumption we have made in all this, that our power converter is in place, and whatever reference the controller is providing to power converter, it is able to generate that voltage. So let us say we have assumed that our power converter is nothing but a gain, let's say not G, but some other KA we can have to remain consistent, and then this reference V star is given and V voltage is generated as output. So V voltage we can say is nothing but K times of V reference, which means we are maintaining the linearity. There are no further dynamics involved in this model. We may have some things which we will see in future, not immediately, but as of now we take the power converter as gain. So how this is being realized, this is what is the topic of interest for the today's lecture. How we are realizing this power converter. Now, first question we all should ask ourselves, being power electronics engineer or at least being electrical engineer, that why we need power converter? What is the role of power converter? So since it's a one-way conversation going on in the online mode, I will continue with this. So power converter is basically required for maybe first requirement what it is having is like the desired voltage should be generated at the output. Now why this is coming up? Because if we look around, we have some voltage sources which have maybe fixed value of output voltage. So which means if we are running a motor drive on any other load and we want to vary that, directly altering the source is a big no, because these are very difficult to change and they have large inertia involved with that. So if let us say you have battery and you want to change its voltage, it is very difficult while the system is running. So if your load needs, let us say 5 volts and your battery is having 10 volts, then you need to do some arrangement to have 5 volts at the load terminal, which is where our power converter comes into picture. Now this is first requirement which it must fulfill. The desired voltage whatever we need must be applied to the load. There are some more additional things which are there. The secondary things could be that the voltage regulation, which means if there is change in current, still the VO should be maintained irrespective of the load current. Now of course this will have some limit, but within the power rating if we talk, then even if we change our current from 0 to let's say maximum value, this VO should hold its value. That should not change. Now, the third requirement is it should be efficient. Let us say we are running all these motors, drives, and all these things for what? For attaining a good efficiency. So good voltage regulation and good efficiency are two secondary requirements but are very, very important. If let us say our efficiency is very poor, something close to 10% or 5%, then this is not a product which can be used anywhere in the industry or any other place. It's good for nothing. So which is why apart from maintaining this first requirement, we have to fulfill these two secondary requirements as well. Now let us see one by one how we can do that. So in short, we have the voltage source. Let's say I make it a generic voltage source. And we have a load. I'm not specifying what load, but this is something which needs some VO output. Whereas our source is having a voltage of VG. So this intermediate entity what we are adding over here, let's call it a black box. This is dropping the rest of the voltage VG minus V0. So when it is dropping this voltage, it is ensured that the other two requirements are also taken care. Now, the simplest thing what can come to our mind for this kind of arrangement that the black box could be as simple as a resistor connected in between the source and load. So let's say if your load is actually a resistance of value R and you want to put some voltage across it, then the rest of the voltage Vg minus V0 should be dropping across this another load R1, and for this current I1 you can work out what is the value of R1. So for this particular current I1, the R1 will be maintained such that the output gets the voltage of V0. But the problem here is the moment this R changes and this current changes, we need to vary our R1 as well. It cannot remain constant. So the voltage regulation is very, very poor. And the second thing, efficiency if you talk about. Now, what is the power output over here, which is V0 by I0? And let's say this is I0. And what we are having is VG by I0. So this efficiency is best, like is close to 1, only when we have V0 very, very close to VG, which means our I0 will be tending to 0. So only for this arrangement, this gives a very good efficiency, close to 1. Otherwise, if let us say you have resistance R and you want to have 5 volts from a 10 volt source, then the R1 should be equal to R for equal division of the voltage, and then our efficiency is nothing but 50%. And voltage regulation, of course, is very, very poor. The moment our this value R changes, everything goes for a toss. So that time even we will not be applying the desired voltage V0. So then what it means that okay, if you want to apply this voltage for irrespective of any value of load current, then we should have some way to vary this load or vary this R1, not the load. So a variable resistor could be there to take care of that. Let's say I call it RV, the load resistor is RL. Now again the issue is efficiency is still at best you can have 50%, or maybe if you are having very, very close operation of your Vg and V0, then probably it may reach 1 for Vg tending to 0 or vice versa, V0 tending to Vg. So we are seeing that even if we are able to maintain the voltage output V naught, our efficiency is still poor. Now let's say if we keep efficiency aside for some time, now how do we realize a variable resistor? We cannot be sitting there varying manually the resistance value while our load is running. So we have to have some arrangement to realize this variable resistor. Now typically we can have a BJT, let us say operating in the linear zone or in the active zone, where this VCE voltage is dependent on how much IB you are injecting. So there is a linearity between the IB injected and VC drop across the device. So this could be a good option for having an automated system for the variable resistor. So we have IB injected on basis of this VO feedback, and then this VC is maintained exactly equal to VG minus VO. So this we are able to realize. Now we can have our motor drive with this power supply. Now typically these are called linear power supplies. So we have taken care of two things in this linear power supply. The desired amount of voltage is applied and voltage regulation is also good. So these two things are satisfied. But the third and another important aspect, efficiency, if you see, there is always a power loss which is equal to VC into the I load. So if your VC is having a good value, let us say we are talking about VG minus VO, and if it is typically of the order of 50 volt and we are drawing something like 10 amp, then our power loss is 500 watts in that power transistor, which is a huge amount of power loss or a huge amount of power getting dissipated in this device. So to maintain the temperature, to maintain other things, other parameters, we need to put a big heat sink to dissipate that heat or that power which is generated to environment. Which means to keep the device cold, we need to have a big heat sink to dissipate all this power, 500 watt. Which is why we see that all the linear power supplies which are available in market, those are very bulky. The reason being they have big heat sink which they cannot avoid. So all other components aside, this itself is the most, you can say, the space consuming component of this linear power supply, and it's very heavy also. So that is why we have these kind of power supplies which are very bulky, very inefficient, and which is where we need to have some arrangement to have better efficiency as well, apart from the other two requirements which we are getting. Now one thing, if you notice over here, when we talk about the power loss, let us say our device is depicting a resistance, then the power loss is I square R. Now, this power loss will be very close to zero for two cases. When our R is very close to zero and our R is very huge, let us say infinity, that time our current goes to zero. So in these two conditions, under these two conditions, our power loss will be very close to zero for the device. Now this is the basis of another philosophy which we are going to use over here for realizing our DC-DC power converter. Now assume an arrangement where we have, let us say, a battery. And we have a switch which is having three terminals, let us say, a pole, throw 1 and throw 2. And this pole can be connected to either throw 1 or it can be connected to throw 2. This is the single pole double throw switch we are having here. Now, let us say if we have such switch in place and we are connecting our pole with throw 1 and throw 2 in sequence, and we are repeating that process at pole P, what voltage we will be getting. So this will be of nature, which is a pulse DC voltage. So we will be applying the voltage for some time. The VG voltage is applied for some time, and for another time it is shorted to T2. That time the voltage is 0. This is PT1 and this is PT2. And this is repeating. So we apply this for number of cycles. Now, if I ask you that what is the average voltage applied at the load, let us say VO average, and we have, let us say, these time periods defined very well. Let's say this is T on and this is T off. And total time, this TS, let's say call this switching cycle time period, so which is maintained constant. Our T on T off may vary, but we are maintaining TS somehow constant. Now, our VO average we can write in a manner that we are applying VG for, let us say, T on time, and then we are applying 0 voltage for the rest of the time, T off, and it is getting averaged over the time period Ts. Now, this gives us the average voltage of Vg into T on by Ts. Now, you may call this T on by Ts as the duty cycle for this switch. So, this can be called as D, the duty ratio or the duty cycle. Then this gives us very famous equation which we all know from our previous courses, which is a buck converter equation. Now here if you vary D from 0 to 1, we can get the VO average from 0 to VG. This is what the basis of our new converter philosophy, what we are having. Now there are few things when we are having this kind of arrangement. Yes, on an average we are able to get this voltage V0. We are having this switch which is operating very fast. Let us say this time period is of the order of some tens of microsecond or maybe hundreds of microsecond at the most. And then we are able to operate this and we are able to get this kind of voltage at the output. Now, can you apply this voltage anywhere you want? This is the first question. Yes, we are able to get all these things and there is no power loss. There is nothing happening because this switch I am considering is like an ideal switch where there is no resistance and no current flowing when it is open. So now if we want to apply this voltage, which is a pulsed DC voltage having some value at for some time period and then 0 for another time period and again some value for another time period, and this goes on. So this voltage we need to apply to, we want to apply to some load. Then what that load could be? So if that load is, let us say, a resistive element or an RL load, then yes, there is no problem in applying this voltage because whatever you apply to resistance, the current will follow the wave shape. For RL, it will be little more smooth. There is no issue in that. So we can have this arrangement connected across a resistance directly. No problem here. This is fully allowed to have for the resistance R or even for RL. But the moment we have any load which has a battery or capacitor component, that moment itself, this is a big no, because we will be shorting two different voltages if we connect this pole to throw one or even to throw two. We will be shorting two different voltage levels. So in first case the VO will be shorted to VG, and the second case VO will be shorted to ground. So both these states are disastrous for this converter. So this is not allowed. Now what do we do? If we have only limited options for the load, then our power converter also has limited application. It cannot be used for a generic purpose. But we all must have some solution always. Now here the question comes. Let us say in nature or in general, if you say you have different type of power sources. So it could be a voltage source or it could be a current source. In general, we can have two power sources, electrical power sources. Now, what is the condition of power flow between different power sources? So let us say we have a voltage source Vs1 and another voltage source is there Vs2. So can we have power flow between the two voltage sources? On the other hand, let us say we have one current source and we have another current source. So can we have power flow between two current sources CS1 and CS2? Can we do that? No, it's not allowed. Why? Because the moment you try to short two different voltage sources or two different current sources, you will be destroying both. At the most, we can have Vs1 equal to Vs2, but then the power flow is 0. Same here, if we have CS1 equal to CS2, power is 0. So which means we need to put again some dissipative element which will drop some voltage or no, take some current in shunt, and then it will allow the power flow to be smooth. But then the efficiency will go poor. Now, what options do we have? So one simple arrangement if we make, let us say we have a voltage source available with us and we have a current sink, let us say, or current source, whatever way you call. So because this can never be opened, the current source, so always we will have a switch which will definitely close the path. So let us say we make the arrangement like this, using the SPDT switch. Let us say we make the arrangement like this. The voltage source cannot be shorted, current source cannot be opened. So either we connect the current source to the voltage source or we short the current source. So is this allowed? Is there any problem in this? So we'll see that any of the criteria for voltage source or current source is not violated, which means this is perfectly allowed. We can short a voltage source and a current source together. Why? This has requirement that the current cannot be changed, I, and this has requirement that voltage cannot be changed. So we are having the current flow of I and having the voltage of V, which is not disturbing any of the properties or any of the principles of these two sources, power sources, Vs and Cs. So then we can say that this is perfectly allowed, and this is the way how we can have power flow between two power sources, or maybe a power source and a active power sink. Now the question comes, first thing, in nature we have voltage sources. There are many, like you have battery, you have solar panel, or even you can have diodes rectifier. If let us say in particular I am talking about the DC power, DC voltage source, then you may have diode rectifier connected to the grid supply, providing an stiff voltage. So all these arrangements you can make very easily to have a stiff voltage source. Now, what about the current source? How can we realize that? So the current source is nothing but a stiff current element. Let us say by some arrangement, if I make the current in this circuit constant, let's say I naught, and there are no dissipative elements in this circuit, the current will keep on flowing forever. And if you are connecting this to another circuit and somehow you maintain this average value of current, this is as good as a current source. So the nearest thing what we can think of for this arrangement is an inductor. So this inductor, if let us say we have arrangement such that we are applying the voltage for some time. This is our voltage source which is having a voltage V, let us say, and we connect this switch P to T1 for some time, and then we disconnect and connect to T2. So this transition time is 0. That's what we say. So that this current source is never open. Let's say the value is L. Now how the current will be maintained? So, and this is once we are doing, we are just connecting to T1 for some time and then we are connecting it back to T2. So now what will happen? The moment you connect to T1, you have some voltage across the inductor. Now this voltage will give rise to current and it will reach some value. Let us say this is my desired value. And after this, I disconnect the T1 and connect it back to T2. So now my applied voltage is 0. And so there is no way in which the current can change. So it will maintain this value I naught or I whatever it has reached. So this is how the current will be maintained in this inductor. So we all know that this is the governing equation for inductor, which means if let us say we want to have any abrupt change in current, we need to have infinite value of voltage over here. So our current cannot be discontinuous. We will need infinite amount of voltage to alter any current in inductor abruptly. So we cannot have any current like this in inductor or any discontinuity in the current. So then with the reasonable value of voltage we can maintain. But now the condition here is that this DC voltage we should not have for very long time, which means if let us say in our system we have DC voltage applied for a very long time, then the inductor current will keep on rising and it will go to a dangerous value. It may saturate and then it may burn. So if this is our voltage VL, then this is how our IL would be. So we have to have some limit on the VL. Now, if this equation we solve and write, di by dt, and this we solve. So what we will get basically the I value will be equal to some I naught, let us say if that is the initial condition, and then now this is very important thing to understand. If we want to maintain this current to the average value I naught, then the other term, this term in yellow circle, must not have any average value, which means what? The average value of this VL dt, this must be 0. This is the famous volt second balance principle for the inductor. We must have the voltage into second balanced for this, for any inductor to have a DC value of I naught. Now this will be the basis of many derivations in our power converters as well. We will follow this principle. So now, once we have decided that okay, our current source, let's say this, can be realized in this form, so which is not exactly a source, but we can say shorted inductor, but the current is maintained somehow. So then we can realize our converter fully with this. What we do at the pole, we connect this inductor. So pole is never disconnected. It's always connected to either T1 or T2. So that way we maintain the current in the inductor, and this side we have load. It could be a resistive load or it could be any other active load, let's say battery or capacitor or anything. It could be here. Now what we will ensure in this, that we are having this principle intact when we are operating this circuit. So let's say, for sake of completeness, we have the capacitor also connected over here, and then our resistive load connected over here. So what this capacitor will do, this will maintain the voltage, output voltage at some value. So similar to what inductor is current stiff, the capacitor is voltage stiff. So assume that it is maintaining the output voltage at V0. Now we can apply our volt second balance, and what we can find, let's say this is Vg. So this is connected to T1 for some time. And then it is shorted to T2. So then this is the case. Now if you check the VL voltage, the voltage across the inductor, what it is, that for this duration T on, it is Vg minus V0. And for this duration T off, it is minus of V0. So Vg is not applied over here. It is shorted to ground. Now sum of these volt seconds should be equal to 0. This must be equal to 0. So if we solve this, we will find again our famous buck converter equation, that V0 is equal to T on by T on plus T off times of Vg, or in other way we say the duty ratio of the switch PT1 into the input voltage. So this is the generic realization of our buck converter. So far we have not said anything about what this PT1 or PT2 is. So irrespective of what device you are having today or 50 years back or maybe 50 years in future, this is not going to change. This is the generic concept which is independent of what device we are having. Of course, there will be some definite properties required for the realization of PT1 and PT2, which we will see in subsequent lecture. But apart from that, this is a very generic realization of a converter. Now here one thing I have mentioned, that at the output we have voltage stiff element capacitor. The voltage output is V0. Now what do I mean by voltage stiff? So again, how we have governing equation for the inductor, we have governing equation for the capacitor. So which means there cannot be any discontinuity in VC. So if you want to make any discontinuous waveform for VC, your IC will go very high. It will be close to infinity. In other words, if you solve and write this, so if VC you want to maintain to a value V0, then this is the equation which will govern that, and to maintain it to the average value V0, we must maintain this other term close to 0. So now either you can call this average value of this equal to 0 as charge balance, or you can call it amp second balance. So this is dual of what we are seeing in the inductor. This is dual of inductor. So whenever we are having any capacitor bank in our power converter, we must maintain this rule. This is our principle which must never be violated. Now we move to the next one. Let us say what we have done in the present scenario is we had one voltage source and we had one load which is a current sink, you can say, which is taking power from the voltage source. So power is transferred from the voltage source to the current source in this scenario. This is scenario 1. Now we may have another scenario where the current source is actually sending power back to the voltage source, which is possible. We may have regenerative loads, let's say DC motor, so that may send power back to the voltage source. This is scenario 2. If I rearrange this, so it can also be shown in this manner. This is what is our, let's say, when we have voltage source to current source power flow, this is something where we have current source to voltage source power flow. So let us see what we are getting in this scenario, the scenario number 2. Now we have some current source which is maintaining a value of I0, and then let's say our load which is a voltage stiff element, let's say a capacitor connected with some load, and then it is having a voltage output of V0. Now what will happen? We will be applying the current in a pulsed manner to this capacitor. So if you see, this is now pole P, throw 1, throw 2. So if you see the load current, how it will look like. Load means the combined thing I am saying, capacitor plus resistance. So you can call it PT1 current, IPT1. So that will look like I0. Let us say you first charge this and then discharge into the load. So that is how we maintain. So we are maintaining the current for some time in the current stiff element, and then we are injecting that current to the load. Again, we are maintaining that for some time and then we are injecting it to the load. So what we are doing, this value here is I naught. So on an average, we are applying a different value of current. Now, what is that value of current? Again, similar to what we have seen in the very initial thing, the average value we can compute. Average value of this is load. Don't confuse IL with inductor here. This is I load. So the average value of I load will be 0 into T on plus I naught into T off by Ts. This will turn out to be I naught into 1 minus D. Which means if our D is varying from 0 to 1, our I load average value will vary from I naught to 0. So this is what we are doing in this structure. Now, we have seen that any other intermediate component is actually not dissipating power, which means what we have, that power input is going equal to power output, which is true for both the previous converter, which was like voltage source to current source, and for this also, which is current source to voltage source. So if this is true, let us compare for both the converters what is happening basically. So in one case we have, and second case we have current source to voltage source. So first case what we are doing, we are having V output equal to D times of Vg. Here what we are having, I output is equal to 1 minus D times of I, let's say source or Ig. Now because for both the cases P in is equal to P out and here also P in is equal to P out, what we will have, that current output will be equal to 1 by D times of current source, and here what we will have, voltage output is equal to voltage source divided by 1 minus D. So we were doing the buck operation on the voltage over here and we were boosting our current. And here we are doing buck operation on our current and we are boosting our voltage. So if we take output voltage as reference, very popularly we call this converter as buck converter and this converter as boost converter. So for clarity, I will draw both the converters again here. So one side we have, let us say, a battery, and then the current stiff element connected to the capacitor and the resistance. And here we have the battery connected to inductor first, because this we have to realize as a current source. And then this is giving power to the voltage stiff element, which is a capacitor connected with the resistance. Now here we can never ignore resistance, because if you make R value very high, let us say 10 to infinity, you will keep on injecting current to the capacitor and the voltage in the capacitor will keep on rising. And it may go to very dangerous value. So boost converter, we must not operate without load. This must have a load always. This is the requirement for boost converter, whereas this is not so for the buck converter. You may have R value infinity. So these are the two basic converters which we have seen in our previous courses, but this is a different perspective which I wanted to put in front of you related to these converters. Now, so far we have not said what is there in the SPDT switch over here or over here, whether it's a diode or MOSFET or BJT, and where it is connected, how it is organized. This and all we will see later. But on basis of this generic switch SPDT, we can realize both buck and boost converters. Now, there could be some converters where instead of, this is all single stage power conversion. So whether we are going for current source to voltage source or vice versa, we are having only one stage. Now there could be power converters which have double stage power conversion. Now in double stage power conversion, what we may have? We may have a voltage source transferring power to current source, and then we may have a voltage source receiving power from this current source. So this is something, or it may be vice versa. So this is something which comes under the multi-stage power transfer, and this particular case is double stage power converter or power conversion. Now, which is the simplest example for this? Then if you try to think in that manner about this one particular arrangement which I am drawing over here, we have a voltage source having voltage Vg. We have the current strip element connected in the middle now. So here is the pole. Pole is always connected to the current strip element. Please remember, always. So wherever is your inductor, you will always connect the pole with that, so that inductor is never disconnected from the circuit. It is always in the circuit. So P is always either connected to T1 or connected to T2. There is no transition time in between. So then we have the T2 connected to the capacitor bank and resistance R. So now let us see what this converter is doing. So again, our basic principles are same. We have to have this maintained, the volt second balance. Now if you apply that volt second balance, what you will see that first it is getting connected to the source, let us say. That time the load is disconnected. In the second state, the source is disconnected and the inductor is connected across the load. Now let us say what is happening. Let's say our output is V0 and input is Vg. So we apply the volt second balance. This is for t on time, this is for t off time. And what we will have is VL into VL1, let us say, into t on plus VL2 into t off, that should be equal to 0. And VL1 here is simply Vg into t on plus here it is V0. So V0 into t off equal to 0. If you rearrange this, your V0 will come as T on by T off times of Vg, but with a negative sign. So remember that negative sign over there. Now this is your famous buck boost converter, or we also call it flyback converter. So it is having both the operations. If you write in terms of duty ratio, it is having this arrangement Vg. Definitely notice the sign which I am putting again and again here. So this is how we have the famous buck converter realized. Now what is the meaning of this negative sign? The meaning of negative sign is that when you are charging this inductor, this is the direction of current. And it is going to maintain this direction even when it is connected to the load. So which is why the capacitor is charged in this manner, which is why we see the polarity coming as negative in the buck boost part. So now with this we have kind of realized all our converters, and we are ready to go ahead with the realization of the SPDT switch. But one more thing which I would like to point out over here, that definitely you all should try to draw the waveforms. Let us say when you talk about the buck converter and you have the VL coming with time. So what you have, that you have VL positive for some time and negative for another time, and this is repeating. So you should try to draw how the inductor current looks like. Let us say this is Vg minus V naught and this is V naught, of course negative. So we will have the inductor current rising in this half cycle and falling in this subcycle. So because we are maintaining the same average value, so this starting and ending point at the end of Ts must be same. So if I call this I minimum and I call this value I max, then it is going to come back to I minimum always in the steady state condition. And this is true for all the converters. All the converters must maintain this condition. The current has to come back to that value, which means the average value of IL should be I naught, your DC value of inductor current. That is always true. So this is one thing I wanted to say. So for all the things, all the converters, buck boost and boost converter, you should try to draw these waveforms on your own just for exercise, and you will understand more how these things are coming up into existence slowly. So nothing is random in power electronics. Everything is very well organized, very well thought of, and we cannot have anything just coming out of blue from somewhere. Now, the last thing, because we have been saying that VO is somehow related to your input voltage with some proportionality constant. So let's say this proportionality constant is your V reference times of Vg. So if you correlate with our original equation, V star into K, so this K is actually our Vg, which means this is our converter gain. The K is Vg. And this is your input which you are giving. Now how we are doing this, how we are operating this switch in an automated manner. So typically what we do for operating this SPDT switch, we must have some condition, and that condition is, let us say you have a sawtooth carrier having a frequency Fs, which is 1 by Ts, the time period of this cycle, and you have a reference voltage V star getting compared with this sawtooth carrier. So what output you will get over here will be your gating signals. So whenever our V star is greater than our carrier, we keep our switch on. So whichever is the active switch, let's say this is our main switch which is connecting to the source or charging the circuit. So then we connect that. And then for the rest of the time, we keep silent. So which means connecting the other switch. And this cycle repeats. So what will happen? This is what is your average output voltage coming up. So if you vary V star, your output voltage V naught will vary in a linear fashion. So if you vary this V star from 0 to 1, the V out we are going to get from 0 to the full value Vg. So this is what is the linearity which is the requirement of the controller. This must be maintained. If we are applying a V star, then we must have the output voltage corresponding to that V star, irrespective of how many times we are crossing that same point. So repeatability is very much important. So which is maintained like this. So then we have realized in a generic form how our power converter should be. So in case of DC motors, let us say separately or any other excited DC motor, If let's say we talk about buck converter, we may ignore the capacitor branch over here. So we may have directly our machine, because this itself will have some amount of armature inductance and resistance, and then the EB coming over here. So this could be a simple arrangement how our power converter and our motor are connected to the source. So for case of motors, we may ignore this DC bus. I mean the DC capacitor over here. So this could be one typical example how we connect our power converter with the DC motor. Now the next thing would be to realize this switch, and this is very important aspect for realizing any power converter. So how do we realize the SPDT switch or any other switch? That we will look into the next class. So I hope this was useful for all of you, and you must have got some different perspective of about the power converter and how we should look at them. So the complete realization we may have in the next class. So any doubts, any questions you may ask now.